Okay, so we're beginning the afternoon session, and I'm delighted to introduce my co-organizer of this program, Fabian Ruehle from Northeastern. So a real pioneer in the use of reinforcement learning and machine learning to solve problems in physics and mathematics. That's what we'll talk about.
All right. Thank you very much, Mike. Thank you all for being here. As Mike said, I want to talk about ways to get rigorous results from machine learning using reinforcement learning. And that was the topic of a paper that we published more recently in Nature Reviews. And for the purpose of this workshop, we had sort of a very diverse set of AI plus math, where math was many different subjects. So I pulled examples. One is from a number theory, and two are from knot theory or low-dimensional topology. But this is my set of collaborators. This was done in collaboration with Sergei Gukov, Cyprian Manolescu, Piotr Zuchowski, Jim Hausen, Brent House, and of course, some AI collaborator. So essentially, if you think about sort of the most naive way you could use machine learning for mathematics, or just in general, the most naive way it is used in a classification problem, you show it an image and you ask it, is this animal a cat? You put it into some neural network, which is a black box, and it outputs a probability for it being a cat. So in this case, it's 97% sure it's a cat, and 3% it's not. Good. So of course, you know this works incredibly well in all self-driving cars, and predicting the next word in the Oxford English Dictionary and ChatGPT and all these things. This works incredibly well, this classification problem. But it's not really what we want for mathematics. So let's say you give it a go board and you ask, is there a winning strategy for white from this position? And let's say, again, the neural network has some probability for yes and some other probability for no. But of course, this is not an interesting result in any way. We are not learning. This is a black box. We don't know how it came to this conclusion. We don't know whether it's even true or false.
It's almost the same numbers for the cat and for no. If there's some reason behind that.
Yeah, this was a laziness when I did the slides.
Okay.
So good. So from a point, sort of, yeah, this is not useful. And sort of the only way it would be useful is we could open up this black box and understand it better. But of course, that is notoriously hard to do. And I mean, even if the answers are 100%, we wouldn't learn anything. So this reminded me the situation when I was a kid. I grew up with a Futurama, and it's like these two bots playing chess, and he sits in front of an unopened chessboard, and he says checkmate in 134 moves, and the other one says, okay, you win again. So that's as much as you would learn from observing this conversation.
That's a very long chess game, 140 moves.
Well, it would be interesting to know if there was a winning position for white in any number of moves. Maybe it's 143. So that's a prediction.
All right.
I think if you watch, I mean, I don't know, if you watch Stockfish players, so it directs out forever in the end game.
That is true.
Yeah.
We're human.
Yeah. Anyway, so if you wanted to use this for mathematical questions, or you give it a collection of mathematical objects and you ask it, does mathematical object O have property X? Again, sort of, this is useless, this classification task, because we wouldn't learn anything from it, and we wouldn't even know if it answered 100%, you wouldn't even know whether we could trust it. So for the problems that I want to talk about, we set up a different algorithm. We set up essentially this way of solving discrete math problems. And the way we do it is that we formulate it as a reinforcement learning problem and then sort of throw RL at it. So yeah, we want provable results. And we set up the algorithm such that it solves a binary decision problem, just like we've seen here. Does object O have property X? And the way we set it up is that it is supposed to halt on the yes instances and produce a true certificate for whatever it says. So we don't want it to just say yes, we want it to say yes, and here's how you see it. And we don't make any assumption for the no instances. So it can run forever on the no instances. In practice, it doesn't do that. In practice, sort of, we know where it's going based on the reward that we engineer for it, but we don't make any assumption about what the no instances of the decision problem are about. So that's the setup. And yeah, so as I said, we sort of map we map this problem onto a Markov decision process, and we solve it with a reinforcement learning. So the way this works roughly is as a comparison with Go. So in Go, essentially, you have a state space, which is sort of the configuration of all legal Go boards. You have an action space, which is the sort of the legal moves you can get or you can perform from a given position. You have a policy network, which essentially tells you how to select the next move based on the position that you're in. You have a reward function, which could be like 1 + 1 if you win and -1 if you lose. And sometimes you also have a value function, which tells you how good the position is you're in. So now we take essentially our problem and we sort of map it onto this. We find a state space, an action space, a policy, a reward function, a value function. And then we solve it with reinforcement learning. That's the idea. So the first example I want to talk about is a certain type of Diophantine equation that we got out of string theory. So the setup is essentially in string theory, we assume you have 4 non-compact dimensions and 6 compact dimensions, which are modeled as tori here. And then the way we want to encode the physics that comes out of this is in terms of so-called brain stacks. The details are not important. The important thing here is we have a 7 tuple of numbers that encode essentially the number of brains. They're all integers, and these are winding numbers around the A and the B cycles of the tori. So we have an ordered 7 tuple of integers, and then we can have multiple of these. And then you just give this into your string theory, and you ask sort of what assignment of integers to these numbers gives you a consistent theory, and this then turns into some Diophantine equations in these 7 S parameters. And this is something that people have worked on for a long time, and probably so Mike was very involved in this, and people have studied this particular system very, very well. So when we started doing this in 2018 with Jim, we wanted to do something that was sort of where we had statistics on how many solutions there are and how they are distributed and so on, so that we could compare how well the reinforcement learning does compared to brute force searches that had been undertaken in this right now. Good. So the way we map this then is the states are just the ordered 7 tuples that describe the brains. The actions we took were just sort of, you can increase or decrease any of these numbers by 1. So there are just 7 as actions, or 14 as, because you can increase and decrease. Terminal states of your reinforcement learning, that when you won or lost the game, this just means that all of your consistency conditions are satisfied. And as a reward, we just took the distance from the solution, meaning you have a bunch of equations, you can put these numbers in, you see how far they are from being satisfied, and this we used as a reward. So typically in RL, you often have very sparse rewards. If you play a game of chess and you only reward at the very end, you need to play until one of the person is checkmated in order to then say, okay, you get a +1, you get a -1. So if you want to play this until the end, you might play a very long time. So in this case, we have an intermediate measure of how good we are. And of course, this might be somewhat erratic. It might be that sort of you need to go further away from the solution. You need to violate the equation more before you can satisfy it. But the way this is set up in reinforcement learning is you're not rewarding on the intermediate next step, but you're rewarding what's called the return, so the sum over all the rewards. So if it can get to a winning state, but has to sort of make the distance larger before, or make the punishment bigger before it can get a bigger reward, it will do this in the end. This is how the algorithm is set up. So here's the example. You get these types of Diophantine equations that I wrote down. I just call them conditions 1, 2, and 3. They have a physical meaning, but that's not important here. So all I wanted to sort of flash were these 3 equations that are equations essentially in these n's and m's that we saw previously. And then we just give this a reinforcement learning agent and we train it to learn a solution. And here's what it came up with. It found sort of after, I don't know, 10 to the 3 times 10 to the 6 steps or so, it started finding solutions and then it finds more and more. And the way it did this was by solving the first condition and then the second condition and then the third condition. And then we were interested in, okay, so how does it do this? How does it solve these Diophantine equations? And actually, as I said, people had studied this before and they had done a brute force search. And what they had discovered is if you had sort of brute force conditions 1 and 2, you could decouple condition 3. So these are coupled Diophantine equations. You see the ends and ends appear everywhere, but people had worked out a strategy so that you brute force this and then you can solve this without destroying the solution to this. And so this was by adding so-called C-type or filler brains. So we looked at what our reinforcement learning agent was doing, and we noticed that around the time that it starts solving this, it's also adding a lot of filler brains at the end. So this told us it learned this human-derived strategy of solving these Diophantine equations initially. But then sort of training continues, and then we found that it sort of did something else. Instead of solving 1, 2, and 3, it first solved 3, then 1, and then 2. And in this case, sort of, there's no known way of decoupling this equation from these equations. So it learned a new strategy, which actually worked better. It found the solutions faster in a few number of steps, and it found more and different ones. But we don't know what it did here. So we couldn't, in this case, we couldn't interpret it. The reason why we could sort of say something here is because very clever people who had thought about the problem previously had figured out this strategy. But for this, we just observed this works well. We don't know why it is, and it's still very, very difficult to interpret the neural network. So the neural network, in some sense, is still a black box. The policy network, in this one case, we managed to interpret it, but in all the other cases, we have no idea what it's doing. We just know it works, and we can, of course, we can look at these rollouts. We can study how it checkmated the other player or how it sort of got to the solution. And that is our truth certificate. So this is how we know that it didn't cheat, because we can just see that all the things it did was legal, but we don't have any idea of how it sort of found this in the first place. So if you have a good enough domain expert in chess, they can look at, I don't know, chess games that AlphaGo plays, and they can sort of see what it does, valuing position over material and so on. But in this case, sort of even with experts, we couldn't really interpret. I mean, maybe we're not experts enough, but we couldn't interpret what it was doing. So this is essentially the best type example that we had. We just started the reinforcement learning algorithm. We found the solutions. We found something we could interpret, and then it found very, very good solutions, but we couldn't interpret them. So that is the number theory problem. So let me move on to the second example, which is the unknotting problem. And the problem there is really just you're given a knot. So knot is an essence. Sorry.
Sorry, I had a question for that.
Yes.
So, did you try, say, the local search methods or like the other search methods? Because, like, say, the strategy of like that you start with a state of tuples and increase the numbers by 1, and this, so you can probably, like, I think, like it is very similar to the problem we did in the graphs and so
Yes.
on.
Yes.
So, like, did you try any local search or like non-machine learning methods here?
That's a good question. In this particular case, we did not. So people had brute forced it, and we just tried reinforcement learning, and it already worked very well. So what we used here was something that's called a A3C algorithm. So when we started this, Jim and I were poor students. Maybe Jim was already a poor assistant professor. I can't remember. Yeah. But so we didn't have GPUs at all. So what we did is we needed something that I could run on many CPUs, and there was no good curriculum learning in here, because if you just have this equation, there's no way of getting close to it. So what we did is we used an algorithm that puts many workers in parallel somewhere into the state space. So you just throw 100 workers into state space, and they start exploring locally, and then they report back. So that's an asynchronous advantage actor critic. So the reward is based on the advantage function. You have the actor critic model from the neural network, but we had also all of these hundreds CPU-driven workers that sort of explored locally already and then reported back to a neural network, but we didn't do a pure non-ML based local search. Yeah, thank you for the question.
People do stuff like that these days, but our point is just to focus on our.
Yeah. So the second example is from unknotting. So what a knot is, it's an S1 embedded in S3. And then typically you take a knot projection like this, and then you ask, is this not the unknot? And this particular case, it's not very, very easy to see, even though it's a very simple knot. But yeah, so this is an example of an unknot. So you can actually manipulate this to become this knot. And again, we map this onto a reinforcement learning problem. So the states in this case are the representation of the knot, like diagrams like this. And the actions are essentially one of the three randomized moves. So it turns out that this problem, first of all, you might wonder whether this problem is empty, whether this is trivial, whether every node is the unknown. Of course, we know this is not true, but randomized proved essentially that you can relate any two knot diagrams by doing one of these three manipulations. So either you essentially take a loop and you pull it straight, or you take this and you move it, and you move these across, or you have a triple cross and you move this strand up and down. And just by iterating on these actions, you can get from any knot diagram to any other knot diagram. So essentially, if you're looking for the unknot, you know that if you start with a knot diagram that's complicated, just by doing these things over and over, you are able to get to the thing that is manifestly the unknot. And just by looking at what it did, this is a true certificate. We look at the rollout of the RL agent, and if we had the thing in front of us, we could literally use this to unknot our knot. So maybe there's some commercial application there.
Yeah, can you control the number of moves?
Can you control the number of moves? Very good. So the way we set this up, this is all encoded in this reward function. So as I said, the way the agent is set up, it gets local reward, and we reward it just by the number of crossings that the knot still has after doing this. Then, so you calculate what's called the return, which is the sum. It's a sum over of all the moves, of all the expected rewards that you will get from now on until the infinity, or until you reach a terminal state. And this is what's called, this is some decay constant here.
Because discount factor.
Yeah. So what we do is we only punish our network because we have no idea sort of how many moves it will take. So we just punish it by the number of crossings that are in the knot. So it will try to get to 0, which is in this discount factor as 1. It will get the least punishment if it gets to 0 the fastest. So in this sense, we are sort of conditioning it on finding the solution as quickly as possible. Yeah, thank you for the questions. Good. So essentially, if you take this knot and you look at what it's doing, first of all, it's doing this poke move. It's moving this part here. Then it's doing one of these moves here. And then you continue, and then eventually you get to this, and then you do the type 1 randomized move, and you get to this, and then you do the type 1 randomized move, and you get to this. So you can just look at what the neural network does, follow this, and see whether or not you found the unknot. So we ran this for different number of crossings. We used a specific encoding of the knot, which is called a braid. I'm not going into details what that is, but roughly this is a lower bound and often a very good lower bound on the number of crossings in the knot, so how complicated it is. And then we tried many, many different RL algorithms for that. And you can see that our baseline study was just a random walk. So you just randomly try to unknot it. This is probably what a human would do. If you just have this complicated thing in front of you, you would just try things. And you see that, and you would expect it tapers off exponentially with the number of crossings. The more crossings you have, the more complicated, the more choices you have, and this just sort of goes down exponentially. And the best performing algorithm was ERPO, that's trust region policy optimization. You saw it could solve 80% of the knots, could unknot in a given time cutoff that we could. We also tried to see what it was doing in order to unknot them, but again, we saw there was a big shift from the untrained, which sort of performs randomly. The distribution of actions that it took varied wildly from this, but we couldn't interpret how it was unknotting it. Yes?
Why is it that's trend up? It likes more complicated brains.
Sorry?
Well, the blue dots seem to trend up slightly.
Yes, that's
Why? Do they like complicated brains?
yes, we observed this. So what we did prior to this, we did what I just told you we shouldn't do. We trained a classifier to classify is this the unknot, yes or no. And we also saw that the accuracy of this working, so this is one, is essentially also was asymptoting towards 1. If the braids came longer, this thing got better That's telling. We don't have a very good explanation for why that is. One thing we observed is if you give it more crossings, somehow it has more data to learn from. So if we sort of if we took away data from the longer braid words, let's say we increased the braid length by 2, but we only give it half as many data sets, then this was a constant. So somehow it learned probably a local obstruction or something, some heuristic from the fact that the longer braid words contain more data. But we don't have a very good explanation.
I guess in this case, it could in principle be statistical fluctuations that we could have taken.
Yeah, but this continued to.
It's quite a, it's quite an increase.
Yeah, I also don't know why. Yeah, I think this is a statistical fluctuation. But yeah, as I said, we also observed this for the pure classification.
So how you are representing the knot, like?
Yeah, I wasn't going. We can discuss this in more detail. So we use something that's called a braid representation.
Could it be purely an artifact that when you have large braids, increasing percentage non-trivial? So if it just says non-trivial all the time, it's highly accurate.
No, so this is what this is measuring. This is in 300 or in n manipulations. Can it get something that is the diagram of the unknot? Can it unknot it? So this means 82% of all the diagrams that are unknots, it finished to unknot in a certain time. This is what this accuracy is.
How do you know whether the diagram represented the
Good. So this goes into data generation, which I also don't have time to talk about. So, but what we did is we took the unknot, we just took the simple unknot, we performed random randomizer moves, destabilization until it became a complicated representation of the unknot. That's the only way, because of this problem. Otherwise, you don't know. If you just generate a random knot, it's probably not the unknot. And in this case, actually, we could do curriculum learning because the way we generated it, we could generate very, very simple knots, and then we made them longer and longer and more complicated. So there was a natural stratification by how many scrambling moves we did. And we trained it on the simpler ones and then in the more and more complicated ones, so that the reinforcement learning agent had time to learn what the actual task is. If you just give this random length 100 knot, it will just get punished and never figures out what to do. So curriculum learning in this case was possible and was very helpful. Yes.
Just following on that, isn't that even strange though? Is that how in solving the one of length 100, it's going to go through a knot length 40, right? Or is it not?
Yeah,
No, not necessarily.
Oh, sorry?
Because we use Markov with the braid equation. Actually, a pertinent question is, when you fed it the trivial knot, was it necessarily the trivial braid, or was it just the braid closure became trivial after Markov moves?
the braid closure became trivial.
So you gave it plenty of examples where the braid was not the trivial
Absolutely, absolutely.
or permutation.
Okay, so this was the second example. The last example is sort of the most complicated one, and this was about ribbon knots. The reason why we were interested in this, Cyprian and Diesel, they constructed a family of links, 3,375. They look like this. So links are just, so you have these three knots, the red, the blue, and the green. And then they are twisted according to these integers here. So they varied ACE from -2 to 2 and BDE from -1 to 1. And by twisting them up in this way, essentially, you got these three links. For the purpose of the project, you could ignore the red one and just study the green and the blues for the machine learning question. So the red one makes sure that they share the same zero surgery. But the point is, if you have the green and the blue link as isolated objects, and one of them has this license property or ribbonness property, and the other one doesn't, then you know that this Poincare conjecture is false. So this falls again into the example of finding a counterexample, as we heard in the nice talk by the Google DeepMind presentation. So they put forward these types of potential counterexamples to the smooth Poincare conjecture, which asks whether every force sphere is diffeomorphic to the standard sphere. And of course, Mike had given us the proof for the topological case previously. And so this is the last open problem of the Poincare conjectures. And it's very interesting because it's false in general, but it's true in 1, 2, 3, and 5, and 6 dimensions. And it's false for, if you replace a force sphere by R4, it's known to be false. So this is very, very interesting. the immediate case. So that's why we were interested to see whether we could prove that one of these knots is the ribbon knot and the other one isn't, because then you could construct counterexamples. It's not very conjecture. And there are also other things that we wanted to test. So up to 14 crossings, people have classified like brute force searches or other techniques, whether these knots are ribbon or not. There's a database, and there's also a family of knots put forward by Charleman and Thompson, which are potential counterexamples to what's called slice ribbon conjecture, which is again another conjecture. So we were interested in sort of studying these examples to make progress and to see whether one of them is a counterexample to these open non-standing conjectures. The way we set up the reinforcement learning was again sort of, so you had a representation of a knot and a band. I will explain what a band is in a second. And the actions were just where to start the band, where to move it, and where to end it. The terminal states in this case was you had to get a set of unlinked unknots. So this problem contains the other problem as a subproblem, the way we solved it. And let me just show you. So let's say we have this knot here. This is a knot that was not known whether or not it's ribbon before we proved it to be ribbon. And now what you do is essentially you start pulling the band. I mean, you start the knot and then you start pulling this down here. And then once you get to, let's say, this point, now you need to decide where you want to go next in one of these adjacent chambers. And you can either move it over or under. So in this case, the reinforcement learning agents tells you to pull this under here. Then it tells you to attach it back up here. Then you get something like this. You simplify it, and then you see you have now an unlinked unknot component. We have the sum of two opposite trefoils. We ask them reinforcement learning, what do we do next? They say, well, you start pulling here, you twist it, you pull it above here, and you attach it there. And now if you look at this for a minute, or if you ask your reinforcement learning agent to simplify it, whether this is the unknot, it'll tell you, yes, it is. And this now proves that this particular knot is a ribbon knot, which was not known. So this is also an example where this worked very well, but already a much naive. Yes.
I just hope you're careful to attach the bands with the correct orientation.
Yes.
Because if the initial diagram is connected, when you do the ribbon, you should get a disconnected diagram.
Yes.
But you said it comes out the square function is connected. You do a ribbon move. But if it's two components,
Yeah, that's why we need to twist here.
No, but the first 4 arrows, is that first diagram connected? It's one component.
This is a two component.
First diagram, same. The first diagram, K14.
This one?
Yeah, that's connected.
That's a knot.
So once you do a ribbon move on it, it should break into two.
Yes, exactly. It breaks into these two components. The blue one.
Oh, I'm sorry. Oh, the blue thing is a component.
The blue one, yeah, exactly. After attaching this, I can simplify. So this is now two components.
I see. I didn't understand. I thought you were just circling one of the components.
No. Sorry. This is Snappy's way of drawing the unknot. Yeah. No, it's a good question. But yeah, every time you attach, as Mike pointed out, you need to make sure that you preserve the orientation and your number of components increases by 1. So we have a 2-component link. After that, we would have a 3-component link, and these 3 need to be unlinked unknots. So we need to run the game. We need to run the unknotting game on all 3 components and make sure that all of them are unknotted. And this is actually so the problem here is we tried many algorithms again. We tried also the AlphaZero search, but AlphaZero essentially attaching is mostly legal. And so after you attach it, you need to check whether you checkmated your opponent. And this is an extremely costly operation here. So the problem we couldn't get AlphaZero to work because it had to do this very, very costly check of whether the state was a terminal state, whether we won the game. It had to do this over and over. It was just so slow that we couldn't get it to work in this case. So we used again other algorithms. We used again other algorithms, but Google the AlphaZero search didn't work for that. Yes, let me wrap up. So let me just say one last thing here. So this is also an example where we could get with reinforcement learning, we could get good results, but we already got good results by we we looked at the rollouts of these. Again, we used HEC. We used, as I said, the out of zero Monte Carlo tree search. We used triple because they had worked previously, and we found that what it likes to do is it just likes to attach a bunch of short paths. And so what we then did is we just made this independent of the state. We tuned a random walker, a weighted random walker, which essentially had the weights here, and we optimized this using the Bayesian optimization scheme. And this worked incredibly well. And it actually worked better than, well, better depends on the measure. But if you measure the timeout, this actually performed better than the neural network, because you had to query the neural network all the time, versus this random walker is state independent, making just drawing the next move from a weighted distribution, but independent of the state. So in this case, it actually worked even better. If you use the neural network, just the number of episodes, the neural network performed a little bit better because it was sort of more informed. It knew the state it was in, but still, it could solve most of, I mean, depending up to 14 crossings, which is the blue line, we could solve essentially all of the ones that were written. So let me skip this and just say, if you want to try it out yourself, I did actually put a QR code. So you can download it from my GitHub and play with it if you want. So let me stop here. I wanted to say that you can use reinforcement learning and rollouts to get provable results. And I showed you how to do this for Diophantine equations for an unknotting problem and for trying to disprove the smooth Poincare conjecture, which of course we didn't find, otherwise you would have heard of it, but we ruled out all the counterexamples that chip in, and these are put forward except for 2. So if you can if you want to have a go at these 2, download the code and run it for longer, I guess. Thank you.